Hi, everyone. Hi, everyone, and thank you for joining me today. I am super excited to introduce IPU, the image processing unit, for the first time here at ITT. Now, I'm going to show a lot of visuals. This presentation is going to get very visual. If you see something you like, don't be afraid to show it. So, video conferencing is more essential today than ever before. Today, more than a fifth of the US workforce is fully remote. That means for millions of people, the camera is important as the keyboard. On top of that, the average professional spends over 50 working days a year in online meetings. 50 days. That's more time looking into a camera than some people spend on vacation in 5 years. And while some people, not naming names, prefer to keep that camera off, the truth is, every minute we're connected, there's a huge amount of video data that is being processed, enhanced, streamed, and stored. That's the context for why the image processing unit matters. Not just for the device in front of you, but for the way we work, connect, and present ourselves to the world. Of course, it's not just about Zoom calls and video backgrounds and background removals. Vision processing is also just as critical, maybe even more so, at the edge. Think about all the systems that need to see and understand the world in real time. We're talking autonomous systems in warehouses and factories, guided by Intel-powered platforms. Healthcare devices, security and safety systems, industrial control, and of course, automotive, that rely on multiple cameras inside and outside a car. Those demand enormous compute to process in real time. In all these cases, the hardware has to make decisions instantly without waiting for the cloud. And in those moments, having high-quality vision at the edge isn't optional. It's mission critical. That's exactly where the IPU steps in. With all these use cases in mind, the implications for the IPU are pretty clear. It has to deliver great vision quality, anywhere, anytime, in any condition, consistent. That means handling the full spectrum of lighting, from bright outdoor sunlight streaming in through a window to dim corners of a warehouse at night. It means capturing and preserving fine details at high resolutions without introducing noise. So what you see is crisp and accurate. It also means creating a lifelike, natural image vivid colors, true-to-life skin tones, and high frame rate that makes everything feels real. Wherever you are and whatever the light is, the IPU makes sure that the image looks its best. So let's take a quick step back and talk about what an image signal processor actually does. Think of it as a sophisticated chain of functions that work together to overcome the many imaging challenges that comes from the scene, the optics, and the sensor. First, the scene itself can throw challenges at us. Motion blur if things are moving, tricky lighting conditions, color variations, and even depth perception. Then the optics, that's the lens system, introduce their own issues like focus problems, lens aberrations, distortions, or vignetting. Next, the sensor itself, the actual chip capturing the image. It has to deal with noise, limited dynamic range, and resolution constraints. This is where the ISP steps in. It processes sensor data and optics effects, reduces noise, and smoothens textures, correcting colors and manage the overall control delivering a clear, sharp, and true-to-life image. Finally, the output is what you see: high-quality video or still images that look natural and crisp. It's a complex process happening behind the scenes, but it all adds up to the incredible visual experience that we all expect today. Let's dig a little deeper and see how the ISP works inside, step by step. Everything starts with the raw input coming from the sensor. After the light has passed through the optics, that's your lens system, which shapes the image, but also adds some quirks. This is how a raw sensor output looks like before being processed, and it's pretty challenging. Raw data typically comes in a Bayer pattern, where each pixel only sees red, green, and blue. Then the IPU will reconstruct the full color image. The ISP then kicks in with sensor and optics processing, correcting lens distortions and preparing the raw sensor data for the next stages. Throughout the entire process, the camera control system is working in the background, managing things like auto white balance, auto exposure, and autofocus, so that the image looks great no matter the scene or the lighting. Next up is noise and texture processing. This is where the ISP cleans up the image, reducing noise with preserving the fine details that makes the picture sharp and natural. After that, it moves to color processing, ensuring colors are vivid, accurate, and lifelike. And lifelike is the key word in this presentation. Remember that. On with reducing noise with our temporal noise reduction, while preserving the fine details that make the picture sharp and natural. Moving on to sharpening, which enhances edges and fine details, making the image appear clearer and more defined. And finally, roughly after, I would say, 100 billion calculations for 1080p per second, all this processing results in the output: high-quality video or still images ready to be displayed. This is how it works. So now, let's take a look at the journey. More than a decade of ISP innovation here at Intel. We started back in 2014 with IPU1, laying the foundations for smarter, faster image processing. Since then, each generation has pushed the boundaries, improving image quality, boosting power efficiency, and reducing latency while increasing the overall throughput. Now let's talk about why integrated ISP truly stand apart. And these are one of the important things to learn today in that presentation. Discrete solutions connected by USB are limited. They can handle basic tasks, but they simply don't have the memory or the compute bandwidth for more advanced processing. An integrated IPU built right inside the platform has direct access to high-speed DDR memory and to all system resources. It can process raw sensor data at multiple points before, during, and after the imaging pipeline. That provides us with flexibility that nowhere can be found in other solutions. It enables workloads that discrete solutions simply can't do, like complex temporal analysis across frames, efficient AI-based enhancements, and real-time adaptations that require close cooperation with the CPU, GPU, and NPU, and all other system resources. This integration unlocks a whole new class of image processing capabilities, delivering smarter, faster, and richer camera experiences that were never possible before. Sometimes the best way to understand the difference is just to see it. So both these videos were captured with the exact same 5-megapixel traditional sensor. The only difference, the image on the left went through a leading competitive discrete ISP. The one on the right was processed, of course, by Intel IPU. Same sensor, same conditions, but look at the result. With IPU, you get crisp details and vivid yet natural colors. On competitive solutions, color look washed out, details are lost, and bright areas are overexposed. This is the power of better processing, and it's why the IPU sets a higher standard for image quality. So we've already seen what IPU can do, and with our latest generation, the results speak for themselves. On Lunar Lake, IPU 7 delivered our biggest success yet. The ThinkPad X9 achieved the highest VCX score ever recorded on a mobile PC. For those not familiar, VCX is an industry benchmark that measures real-world image quality, from sharpness to color accuracy to low-light performance. It proves that when great hardware, intelligent processing, and fine-tuned engineering come together, we can set a new standard for the camera performance in the PC industry. Fast forward to today, and we're introducing IPU 7.5 alongside Panther Lake, our most advanced generation yet. This evolution reflects Intel's commitment to delivering the best visual experiences, balancing incredible performance with efficient power use. It's not just progress, it's a legacy of innovation driving the future of imaging. With Panther Lake, we're raising the bar for visual quality once again. Whether it's bright daylight, challenging low light, or mixed lighting conditions, IPU delivers vivid, true-to-life visuals that preserve every detail and color nuance as the eye see it. This is more than just a better image processing. It's about making every interaction, every call, and every captured moment look its absolute best. IPU brings a set of key architectural improvements designed to push image quality and efficiency to the next level. We've enhanced our HDR pipeline to capture a wider dynamic range, preserving details in both bright and dark areas. Our AI-based noise reduction delivers crisper, cleaner imaging in challenging low-light environments without sacrificing the details. And we've also introduced AI-driven local tone mapping, providing more lifelike contrast and improved depth perception across the scene. All of that is achieved with reduced power consumption, making it ideal for sustained performance in mobile PCs and other low-power deployments. Let's take a look under the hood at the IPU architecture. On the input side, the IPU connects to up to 3 MIPI physical lanes, that's 3 cameras, bringing in high-speed raw data from the camera sensors. Inside, the processing system handles control functions, the hardware pipeline, and line buffering, working together to manage the data flow and prepare it for advanced processing. When more memory is needed, the IPU has direct access to the system DRAM, as we mentioned earlier, giving it the bandwidth to perform complex operations like temporal processing or AI enhancements. Finally, the IPU communicates closely with the CPU, GPU, and NPU, enabling advanced AI workloads and seamless integration with the rest of the platform. This architecture ensures efficient, high-quality image processing, optimized for performance and flexibility. Now, let's zoom in on one of the standout features of IPU, Staggered HDR. Our Staggered HDR captures 2 exposures, a high exposure that reveals details in the darker areas, and a low exposure that preserves the bright highlights. Then it merges those 2 images together, combining the best parts of both to create a final frame with a much wider dynamic range. The result? Brighter highlights without clipping, deeper shadows without losing details, and an overall more balanced natural image, no matter how challenging the lighting is. Let's see an example. So with low-performance HDR, details fade away, as you can see, and the image quickly falls apart. But with IPU, it's a different story. The colors stay rich, textures remain lifelike, and even the smallest details hold up, from the shadows to the highlights, looking vibrant, balanced, and true to life. To sum up Staggered HDR, it's a hardware-accelerated process, so it's lightning-fast and efficient. It supports resolution up to 4K, perfect for today's high-definition demands. And with adaptive exposure control, it dynamically adjusts to changing lighting conditions in real time. Plus, it supports a wide variety of sensors, ensuring flexibility across many camera designs and platforms. And as Arik mentioned before, thanks to our architectural improvements, it delivers up to 1.5 watt power reduction, making it more energy efficient. Shifting gears, let's move on to the next key enhancement, AI noise reduction. So low-light environments often introduce noise, those pesky, grainy artifacts that degrade the image quality. So how do we clean that up? Our AI noise reduction takes on the problem at the source, before even reaching to the IPU. The sensor captures the raw data image and sends it to the system memory. Again, this is unique, usually cannot be done in discrete solutions. From there, the data is pushed to the NPU, where optimized neural networks operate directly in the bare domain. That's before the image is processed, to effectively reduce noise while preserving important details that otherwise would have been expunged in the process. Once the AI denoising is done, the cleaned up data returns to the IPU for further processing. This seamless handoff between the sensor memory, NPU, and IPU enables real-time, high-quality noise reduction that cannot be enabled with discrete ISPs. Here's a side-by-side low-light example of AI noise reduction in action. On the left, without noise reduction, you can see grainy textures, washed-out colors, less details, especially in the skin tones. And on the right, video comes to life. We can see much more details, better colors, and of course, textures are truly reproduced. This is the kind of improvement that transforms everyday visual in low light conditions into truly a professional quality video. Our AI-based noise reduction provides better tone mapping for natural balanced visuals. It supports resolution up to 5 megapixels with 30 FPS, covering a broad range of devices. It provides an improved VCX score, proving real-world image quality gains. And it enables the use of constrained optics cameras, such as camera-banded display or thin bezel cameras, opening doors for thinner, more compact devices without sacrificing image quality. Next up, let's talk about AI local tone mapping, a game changer for delivering lifelike contrast and depth. Unlike traditional global tone mapping, which applies the same adjustments across the whole image, our AI-powered approach analyzes different regions independently. This lets the IPU enhance contrast locally, bringing out subtle details in both bright and dark areas, producing videos that feel more natural. Now let's take a look under the hood. The sensor outputs a raw image data directly to the IPU. To manage computational load efficiency, the frame is being downscaled before being sent to the IPU. The neural network analyzes the image and predicts tone adjustments for each pixel, applying precise local transformations. After that, the processed data flows back through the IPU pipeline for final image enhancements. This targeted pixel-level adjustment is what gives the image its vivid, lifelike contrast. Let's see some examples. Here's a side-by-side comparison showcasing AI-based local tone mapping in action. On the left, without local tone mapping, the image looks a bit flatter, lacking depth and detail in both shadows and highlights. On the right, with local tone mapping enabled, you can see the enhanced contrast, richer textures, and a more natural three-dimensional appearance. This technique really brings the scene to life, making every detail pop, just like our eyes, just like our eyes will perceive it. Our AI-based local tone mapping delivers better, more natural contrast that makes images pop. Unlike older methods, it avoids halos and color artifacts that can distract or degrade quality. It maintains consistent temporal behavior, meaning the image looks stable and flicker-free across video frames. All these improvements combined to give visuals that are not just sharp, but truly lifelike. Now let's zoom out and look at the full IPU software and hardware stack, the foundation that makes everything work seamlessly. At the bottom, we start with OEM reference designs and essential drivers that manage data flow. On top of that, we have a rich set of libraries supporting core imaging functions like 3A face detection, ultra-low light processing, and other functionalities like background replacement, framing, and so on. This stack integrates smoothly with major operating systems, Windows, Chrome OS, and Linux, so it's ready for diverse device ecosystems. And finally, at the top layer, we provide a comprehensive SDK and tools, including camera module development kits, calibration and tuning tools, empowering OEMs to tailor the camera experience precisely to their need. The next generation IPU delivers vivid and lifelike video, no matter the lighting condition. It sets a new standard for image processing performance and quality, powering today's most advanced devices. Thank you.